Andrew and Kath. Okay, no one's probably watching yet, but for the video, I guess. What I ended up doing is, thanks. What I ended up doing is basically converting the box into an RC, and then that way there's no cycles or anything like that. So it worked out okay. It still is obviously not as efficient as if I made everything statically dispatched, but who cares? Hi, Lila. Thank you. Okay, so now what happens now that I fixed this is that we fail because we're passing what the mapper currently thinks is an invalid address, and that is because it is a PPU address instead of a CPU address. So I think we're going to need to do get byte PPU. Because the PPU address bus is distinct from the CPU address bus. Oh, I should also, hang on. Cargo, CPU.rs, lib.rs, nrom-mapper.rs, test, nest test, test donkey, CPU complete beginning PPU. I realized earlier that I didn't have that connected, and so, or I didn't have that committed, and so I was worried I was going to break something and never be able to get back. Never mind, it fixed itself. Yeah, I sort of assumed that it would. Just a delay thing. Okay. Now we need to go into the PPU, and where we have get byte, we're going to do get byte PPU instead, and then we should hit that and explode. Yep, not yet implemented. Okay. And then I thought about this. What we're obviously going to do here is we're just going to push whatever the next thing is, and then push the wait memory one, which is just going to be a no-op. That's how we're going to make that work, but not quite yet. So let's look at the NROM-mapper documentation, because I know these are all slightly different. I think that it will probably work itself out. It'll probably be pretty straightforward because it's the simplest mapper. Here we go, NROM. Also, my cat's on my lap. You can't see him, but he's on my lap. All right, what are we looking at here? All banks are fixed. Program, mirrored as necessary, write protectable. First 16 kilobytes of ROM, last 16 kilobytes of ROM, or mirror. Cat on lap greater than cat on keyboard. Yes, this is true. So when it says CHR capacity 8 kilobytes of ROM, but most emulators support RAM, this basically, so the CHR is the PPU RAM, right? Solder pad select vertical or horizontal. Yeah, okay, so the CHR ROM is what I have here. And I guess that's fine. So I did say that. So get byte PPU should basically be exactly the same. Self.sure ROM adder as usize. And PPU memory map. It looks like there's nothing creative about that. It's just straight up slammed right in place. Not bank switch, CCNROM, which is basically just the same thing, except it's switchable. Okay. So this is just going to live from 0 to 1FF. right? Yeah, NROM is as simple as it gets. But wait a minute, that's not enough room. If I do 8192, see, that's only 2000, which only goes up to the top of the pattern table. There is no name table then. Two kilobytes of RAM dedicated to CPU normally match the name table address space. So I guess that's the name table address space, is this extra 2 kilobytes of internal RAM. Okay. Interesting. So we're just going to call that chur RAM. Yeah, Q8. And then we create you. Chur ROM. We're going to do chur RAM is going to be vec with capacity. Or no, that's not even actually right. So let chur RAM equal vec with capacity 2 times 1024. Chur RAM dot resize with default U8, something like that, whatever, 0. And then chur RAM, slap that in there. Expected 2 parameters, forget how that works. Vec resize, oh, I guess I could call, no, that's not stable. All right, resize width is new length, of course. 2 times 1024. There we go. And then get by PPU wants to do that. Got to make that mutable. And that ought to do it. Index out of bounds. The length is 8192, but the index is 8192 because I'm not actually mapping. So if adder less than 0x2000, then do this thing. Else assert adder is less than 0x3000 and return self.chur_ram adder as usize minus 2000. Oops. Go. Oh, forgot to close the else. There we go. My cat is now headbutting my wrist. So every time I type, I feel like I'm upsetting him somehow. Alright, so we made it to this assert false, which just means that what we need to do is we need to insert the wait mem, which is just going to be an opcode that does nothing. Unlike the no op, which I really should call idle. And then we need to push the next thing, which is something. Sorry, buddy, I need my other hand. Where's that? Here we go. So the next thing is to get the attribute byte. It's the thing that says conceptually this is what it does every turn. There we go. Fetch the corresponding attribute table from 23C0 to 2FFF. Alright. So we're going to do fetch AT U8. And we're going to push fetch AT pixel. And then for PPU op, fetch AT pixel. C0. attribute byte equals ppu dot mapper dot get byte ppu address, and then we're gonna wait mem again, and then what's the next thing? Low background tile byte. Okay, well, we're not gonna do that yet. We're just gonna right, we don't have an attribute byte. Good point. Can I do this? Apparently not. I know there's a way to do that, probably. Rust initialize rest of struct with default. You can define default values by implementing default. Okay, yeah, that makes sense. So you have to kind of do that first. All right. That wouldn't actually help. So, okay. I don't know what I just did there or why I did it. Fetch AT. Okay. The next thing is going to be what? Background tile. Low background tile byte, which is going to be fetch the low order byte of an 8x1 pixel sliver of pattern table from 0, 0f or 1, 1f. Okay. If I remember correctly, when we were looking at the PPU registers, which is in here somewhere, I really need to clean this up, actually. I should just delete everything that I'm not actively using. Here we go. There's like a background pattern table address, which is right here. Okay. Fetch BG low. I'm going to move these wait mems out of the way. They should obviously go at the top because they don't do anything. Push front, CPU, op, fetch BG low, pixel, that needs to go there, and then comma, comma, fetch BG low, pixel, CPU pixel, let base equal PPU dot get BG base. Let adder equal base plus pixel as U16. Dot BG byte BG low byte equals PPU dot mapper dot get byte PPU address, and then we'll just die here. So when we call this one, get anti-base, we want to do exactly the same thing, except that we're going to do it with bit 4. So right shift by 4 and by 1, and it's going to be 0 or 1. Fetch AT redefined. Oh, how did I end up with 2? Okay. Didn't rename this. Didn't add BG low byte. BG low byte. low byte, add the pixel, fetch bg low, go. Panic that assertion failed false, which is what we expect. Okay, we wait for the memory, and then there's something that I wanted to look at here. So there's this inc horriv v loopy v update. So this is the thing that tells you what scanline you're on or something, basically. Increment that. Okay. The low order byte of an 8x1 pixel sliver. Pattern table low, pattern table high, which is 8 bytes higher, I guess. Okay. Data fetched from these accesses is placed into internal latches and then fed to the appropriate shift registers when it's time to do so every 8 cycles. Because the CPU can only fetch an attribute every 8 cycles, each sequential string of 8 pixels is forced to have the same palette attribute. Interesting. Sprite 0 hits. Blah bitty blah bitty blah. Okay. Vertical blanking. What does that H thing do? Does that increment some sort of register that has a scanline counter in it? It's maybe CPU status. It's not mask. Least significant bits. You don't have direct access to the scanline counter, it's internal. Okay, but something somewhere uses it, I guess. Alright, well. Alright, so fetch BG low should do fetch BG high. You can influence it with PPU reg writes. Okay. When you say you can influence it with PPU reg writes, what are you talking about? Do you mean like you can, by like resetting the PPU? I'm confused. My understanding is that it's possible to glitch the counter with certain PPU writes mid-frame. That doesn't sound like a thing that I really need to spend a lot of time caring about. So this should be if pixel is equal to 0, then do this. Otherwise, do the other thing. Which, what's the next thing? another name table byte, I guess. So something somewhere is also happening here. Somebody is copying pixels or something. CPU rendering. Every cycle, a bit is fetched from the 4 background shift registers in order to create a pixel on screen. Exactly which bit is fetched depends on the fine X scroll set by 2005. This is how fine X scrolling is possible. Afterwards, the shift registers are shifted once to the data from the next pixel. Every 8 cycles, new data is loaded into these registers. Every cycle, the 8 X position counters for the sprites are decremented by 1. For each sprite, if the counter is still non-zero, nothing else happens. If the counter is 0, the sprite becomes active. This output accompanies the data in the sprite's latch to form a pixel. The current pixel for each active sprite is checked from highest to lowest priority, and the first non-transparent pixel moves onto a multiplexer where it rejoins the BG pixel. That's interesting. Deal with that later, I guess. 262 scan lines per frame. Each scan line counts for 241 GPU clock cycles. Each clock cycle produces 1 pixel. The pre-render scan line sole purpose is to fill the shift registers with data for the first 2 tiles of the next scan line. No pixels are rendered for this scan line. Still makes the same memory accesses. Okay, so that's what I'm doing right now. So nothing is actually outputting right this second. Obviously something needs to at some point. Two-bit palette attribute for next tile. Next tile's pattern data. 2 bits per pixel, parallel to serial, serial to parallel. Priority mux. 8 pairs of 8-bit shift registers. More importantly, it's scanning OAM for sprites on line 0. Am I even hitting OAM yet? When does that happen? During line -1. Fairly confused here. Alright, so one-bit latch from attribute table. So the name table and attribute table and pattern table are basically the same thing. So every cycle, a bit is fetched from the 4 background shift registers, which I guess are these and these, or these and these. Exactly which bit is fetched depends on the X scroll. Afterwards, the shift registers are shifted once to the data for the next pixel. Every 8 cycles, new data is loaded into these registers. From the latches, maybe? Attribute bytes for up to 8 sprites. X positions for up to 8 sprites. 2 16-bit shift registers. Okay, so ignoring sprites for the moment. 2 16-bit shift registers. These contain the pattern data for 2 tiles. Every 8 cycles, the data for the next tile is loaded into the upper 8 bits of this shift register. Meanwhile, the pixel to render is fetched from one of the lower 8 bits. Okay, that makes sense to me. 2 8-bit shift registers. These contain the palette attributes for the lower 8 pixels of the 16-bit shift register. These registers are fed by a latch, which contains the palette attribute for the next tile. Every 8 cycles, the latch is loaded with the palette attribute for the next tile. So if we look at what I have here, where I called something attribute byte, I should probably call it attribute latch. Why do I have this in here twice? This should go away. Attribute latch, because that's what it is, right? And then these contain the pattern table data, which I don't think I've actually fetched yet, right? Because that should be, is that this low BG tile byte gives the pattern tables? Yeah, and if the register says it's either 0 or 1000, right? Doo-doo-doo. Yep. Okay, so that's the pattern table. And so what we're doing is loading it into the upper 8 bits. There are 2 8-bit shift registers fed by a latch which contains the palette attribute for the next cycle. Every 8 cycles. Okay, where's the palette attributes? Is that this attribute table thing? I guess. Yep. Looks like. Fetch the high order byte of this sliver. So we end up with 16 bits of pattern table, 8 bits of attribute table. And this is 2 16-bit shift registers and 2 8-bit shift registers. Every 8 cycles, the data for the next tile is loaded into the upper 8 bits. That doesn't add up. But I think I get what it's trying to say. So the 2 16-bit shift registers are 2 different tiles, which is this bit, the 8x1 pixel sliver. You end up with 2 8-bit things, and you load them into the high bits of the 2 shift registers, right? What a pain in the butt. Okay, so where does the name table byte go then in this diagram? What does the name table actually do? Fetch it, but then what? Slowly sinking lower and lower. Sorry. Here, let me improve that a little bit. Fetch the corresponding attribute table entry. So I'm not actually doing that. That's dumb. No wonder I was confused. It's not plus what pixel we're on. It's plus the name table byte. Okay, so that makes more sense. So you fetch the name table entry so that you can fetch the corresponding attribute table. Then you fetch the low order byte of pattern table. I don't think you fetch that based on the attribute though, right? Because those go in together into this mess. So you have pattern data and you have attribute data. And the name table controls the attributes. Okay. And then finex picks which bit to go to. And then you mux it with the sprites based on the priority. And then you get a pixel. Okay. And this is happening every cycle, which is why I was confused. Kitty. No, just based on the name table. What's just based on the name table? Sorry, I was talking and didn't see what you were responding to. Pixel's probably the wrong word too, but whatever. Name table selects both attribute and pattern. Oh, okay. So here I need to do BPU name table byte instead of the pixel. Right? Is that what we're saying? For both of these, right? And then we would do BPU name table byte plus 8. Okay. I guess that makes sense. Seems a little weird to me, but it's reasonable. You'd know better than I do. Okay, so that's what's going on here. And then this is going to push, not fetch BG high, it's going to do fetch NT pixel plus 1, except that its super is not a pixel. It's, or it's not plus 1, it's a plus 8, really. What am I even using that for, if anything? I use it for fetching the name table, but is that correct? Probably. Let's see here. Fetch a name table entry, 2FBF, 33 times for each scan line. How much is FBF? FBF. Pattern table is usually in ROM, so it's immutable. Only the name table is mutable for building the screen. Right. Okay. And the name table is indexed by essentially what pixel you're on, right? To figure out what's going on there, you index into the name table by the number of pixels that you have. Yes, but it's not actually pixels because, oh no, maybe it is. Do I want this to increment by 1 or by 8? I think I want it to just be 1. But pixel is like the wrong thing to say. Based on, where is that thing? There we go. Based on this, so we've got like an H count, goes up to 340, and then we've got like a V count, which goes down to 261. More or less pixels divided by 8 plus scroll. Hello, kitty. You're a good boy. Okay, I mean, obviously all of this junk goes away. Okay, so you index the pattern table and the attribute table are basically per bit. And then the name table is a byte. That's what makes it sort of tile-based, I guess. And if we look at this graph, that's why it's every 8. And so when it says inc horiz v, that means like go to the next pixel, basically. Okay. Or not the next pixel, the next tile. Alright, so let's change all these things that say pixel to say tile. Sounds right to me, okay? Right, and then this is dumb. This is not how this works at all. And then literally all this does is PPU Q, push front, PPU op, fetch NT, tile +1. And then I changed a bunch of stuff and didn't update it everywhere. Attribute byte, attribute latch. Okay, I left an H lying around. Unexpected token? What? Oh, I don't have a... Yeah, I don't have a comma. Okay, there we go. So many warnings. I know, I know. Okay, and now we're stuck in a loop forever again. Excellent. So this should basically work, right? Like it should just fetch everything. It's obviously not outputting any pixels yet, and we'll get to that. But this just repeats up until you get to here, 336, which is 42 tiles. Is that right? That doesn't seem right. 2, 4, 5, 6, 7, 8. 336 divided by 8. You see 42 tiles. 336 pixels. But it's 340. Actually, there's this garbage name table thing. So I feel like something in here was telling me about that. Probably in this document. So visible scan lines are 0 to 29. Each scan line lasts for 341 PPU clock cycles. Line numbers here given correspond to how the internal PPU frame counter counts lines. Those last ones are sprite data fetches. Okay. Cycle 0 is idle. Fetch all the tiles. Get fed to shift registers every 8 cycles. Because the PPU can only fetch an attribute byte every 8 cycles. Hi, Nick. Each sequential string of 8 pixels is forced to have the same palette attribute. Man, where were you earlier when I was fighting with RCs and stuff? Presumably living your own real-ass life. I recall seeing a nice image with each PPU cycle described or something. This one? Because that's pretty useful. Yep. I just gotta... I've never really dealt with this kind of hardware before, so I gotta just kind of figure out what's going on. So the data for each tile is fetched during this phase. 4 per tile. Fetched into accesses. Shifters are reloaded on ticks 9, etc. Sprite evaluation for the next scan line is taking place as a separate process independent of what's happening here. Cycles 257 to 320. The tile data for the sprites on the next scan line are fetched here. Again, each memory access takes 2 CPU cycles to complete, and 4 are performed for each of the 8 sprites. Garbage name table byte, garbage name table byte, pattern table tile low, pattern table tile high. The garbage fetches occurs to the same circuitry that performs the background tile fetches could be used for the sprite tile fetches. If there are less than 8 sprites in the next scan line, then W fetches to tile F occur for the leftover sprites because of the dummy sprite data in the secondary OEM. This data is then discarded and the sprites are loaded with a transparent set of values instead. In addition to this, the exposition and attributes for each sprite are loaded from the secondary OEM to their respective counters latches. This happens during the second garbage name table fetch, with the attribute byte loaded during the first tick and the X coordinate during the second. Do you have a plan on how to mode your PPU already? A big match on some state enum. You mean just like in terms of how to make it do things? I'm going to use the same model that I use for the CPU. I'm going to have like a queue of operations to do over and over again, which is basically just a coroutine flattened out. So let's see here. Oh, okay, I see. Increment vertical on cycle 256. This is the unused tile fetch, I guess, because it would be off the end. And then, what are these blue things? These blue things are the spritey stuff? Or just idle, I guess. Oh, there's all this junk too. Gotta deal with that in a minute. Probably go wider on the bus. So then this is all just idleness up until 321. This incvert also takes horizontal, but it won't be visible because V horizontal is reloaded right after. What is this hori T thing? If tile is equal to 256 divided by 8, the blue stuff is the background tile process idle. Right, because there's other shit going on for the sprites, right? It's all this junk. It just has to kind of chill until that happens. Well, the sprite tile fetch process runs. Yeah, that makes sense to me. Okay. Okay. I mean, I guess we can just pass the scan line also to everything. They definitely need to be U16s. Currently, they're only U8s. They won't actually fit. So let's go ahead and do that. U16, U16. U16, U16. U16, U16. U16, U16. This is maybe not the most efficient way to thread this, but it's what I'm going to do. Arg, stop it. 16, U16. Implementing traits for function pointers is Galaxy Brain. Yeah, so the reason that I did this is it prevents a lookup. Basically. You'll only match once at the very beginning of your, like, what am I trying to say? Your, like, list of shit that's happening. I was pretty proud of myself when I came up with this. I have absolutely no idea if it actually performs well, but it seems like it would. Zero, scan line plus 1, else tile, oops, tile plus 1, scan line. Except it's probably not fetch NT. It's probably some sort of like chill out until some sprite stuff happens. Okay. Cat, you are so... Look at this guy. He's just completely melted into my lap. It makes it very difficult to like shift around. He is. He's very relaxed. I wish I was that relaxed ever in my life. Cats have it so easy. Alright. I wish I was that comfortable. Right, Hangman's Moose? Me too. I always wish I was that comfortable. Secondary OAM clear and sprite evaluation do not occur on the pre-render line. Sprite tile fetches still do. Okie dokie. So now that we're done, I wish this thing was a little bit clearer labeled. So that's how these line up. This is the first garbage NT byte fetch is right here. So because these should be the same, actually we don't want this to be where it is. We want it to be 340. 336 doesn't quite work out. It's not an actual multiple of 8 because these last two name table fetches are not used. So, okay. But those will just like bump the tile number. So if we do 336 divided by 8 plus 2, 44. So if the tile is 44, then we restart the scan line. Otherwise, we push fetch NT, and then NT fetch still happens, but it doesn't actually matter because what we're going to do is after the AT, depending on our tile number, we might fetch a sprite tile instead of a background tile. Okay, so if tile is less than 256 divided by 8 sounds like 64 to me. Nope, 32. So close. It's less than 32. Do this. Otherwise, you're going to do fetch sprite low. Oh, and you're supposed to take a scan line also. I should probably make sure that it runs as well as it ever did before I make that change. And it doesn't. I didn't update this for one thing. Tile, scan line. Tile, scan line. I should just make all of these match that. Can I do this? If let, right, so I'll just make these take U6s, even though they don't use them. And then if let tile scan line equal uop.0, uop.1. Is that going to work? I've actually no idea. What do you think, Nick? Is that going to work? Uh-oh. Oh, okay, I see what's going on here. It's because we didn't wait mem. All these wait mems need to have the tile in the scan line passed to them. Maybe add an into to the PPU op. Oh yeah, that's not a bad idea. I'm already doing that once, after all. Is that actually -1? No, it's 0. It's fine. Kitty. Yeah, that's a much better idea. Info from PPU op for U16, U16 from X PPU op U16, U16. Wait, but what's that gonna actually do though? I want to like return PPU, or I want to return x.0, x.1, but it's probably not gonna work that way because it would have worked downstairs. It would have worked lower down if that was gonna work. So how would I actually do this? I want to do like match, and I promise every variant has these fields. Maybe I should just not make it an enum. But no, that doesn't work either. I could make a structure that has the operation and the 2 arguments. And do from on that, and then match on the operation. That's a pretty good idea, if they're all going to have the same arguments. All right, let's do it that way. Struct PPU op. I don't want to change all of that stuff, so let's just do struct PPU state. I don't know, that's not a good name. Op PPU op tile U16 scan line U16. Right, and then we'll get rid of these. We don't need this anymore. And then we want this to actually be... No, I think this is still fine. It's just that we do state, we let uop equal state.op, and then we call it with state.tile and state.scanline. And that ought to work, except that the queue needs to be of those now. Struct PPU. So we had a queue of PPU op, but we need to construct a queue of PPU states. And then obviously that's going to explode unclose close delimiter, or unexpected close delimiter. Okay, why? Oh, because I left this in place. This stuff all goes away. And then everywhere we're pushing the queue, instead of doing it this way, we need to do it the other way. Well, good thing I'm making this change before I implemented 2 god awful much. It's only, I mean, it all fits on one screen of code. That's not too bad. Alright, so we're going to do PPU state op PPU op fetch NT tile 0 scan line 0. Interesting how most arms were shadowing tile and scan line. Yeah, I guess so. Oh, you mean in terms of like not using them? That's true. There's probably a better way to do this than feeding everything through like this, but I mean with the closure parameters, yeah, shadowing them. The closure parameter has to, like you have to pass it in. Otherwise it will capture and then it won't be a function pointer. Obviously the name shadowing is just because I didn't want to give them different names, but then I'm not using it, am I? In most cases, no. But in some I am. And I assume that the number that use it will increase over time. That just seems likely to me. Like, I'm skipping a bunch of stuff right now, and I imagine that a lot of the stuff that I'm skipping will probably want access to the tile and scanline. Although I could be wrong about that. Because again, I don't actually know much of anything about how this is supposed to work. I don't see how you could ever have used it since it would capture and not be a function pointer. So what happens is that this this is on an into or a from impl, which yields a function pointer that has 3 arguments. But then when I call it down here, I pass in the tile and the scan line. So I'm just passing things through the I'm just like threading them through the functions. So I can use it as long as it is a parameter to the function that gets passed in during my execute loop. The stuff in the match pattern is unused here, yes, but it gets used. Originally, it was getting used in a duplicate match pattern, which is down here. You can see it in CPU. But I guess I see what you're saying. Like, I don't actually have to name them in the match pattern. That's a good point. Like, these could be underscores and it wouldn't change. I see what you're saying. Okay. Anyway, what was I doing? Right, I was copying these and pasting them and stuff. Do-do-do. Fetch. BG. Hi. Do-do. 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 And then this one is going to do incoriz. And then this one is going to do fetch nt with scanline +1 and 0. And tile +1 and just scanline. And then I gotta go through and delete all these extra thingamajiggies. What language is this? This language is Rust. If you're not familiar with it, it is a systems programming language with a focus on safety, memory safety specifically for the most part. I like it because it doesn't require runtime, which means that it can be run in like microcontrollers or on the web or places like that. It makes it easy to like embed in things easier. It has a pretty good C FFI story. 97. Oh, wait a minute. But it still has access to like a good type system and macros that work most of the time. and all that. CPU state. No. There's some kinks in the FFI story for panicking across function boundaries. I mean, across FFI boundaries. Yes, I think that is true. Although, somebody, who was that was doing horrible things at RustConf about like throwing exceptions from Rust into C++. But so I think that there are some things that one might do about that. But I basically feel like if you've panicked, you've already failed. All right, let's make sure we reach. Let's make sure we reach here. Okay, good. Let's make sure we reach here. Okay, good. And then you proceed to write a panic. Well, like, yeah, I failed. I just wanted it to die at that point. Alright, so this is fetch sprite low. There's definitely a more ergonomic way to do this bit. I could write a macro. I could even just write a function, honestly, that returns a PPU state. I probably should do that last thing, but whatever. What did you error out? Oh, okay. Fair. Fetch sprite low. CPU tile scanline. Panic. You can just write tile instead of tile. Yes, that is a true thing. Okay, so we are reaching here as our tiles get high enough. Now let's look at how this actually works. Garbage name table, garbage AT, low sprite tile byte. So how does this work? Kitty, 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 kitty. Tile data for sprites on the next scan line are fetched here. Again, each memory access takes 2 PPU cycles to complete. Garbage name table, pattern table. Pattern table tile low, pattern table tile high, but instead of using the name table, what do we do here? If there are less than 8 sprites on the next scan line, the dummy fetches to FF occur for the leftover sprites because of dummy sprite data in the secondary OAM. See sprite evaluation. Alright. Operation done by the PPU once each set line. Prepares the set of sprites and fetches their data to be rendered on the next scan line. So first it clears the list of sprites to draw, which I guess is this junk. Sprite evaluation for next scan line is in the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, I guess, sprites before that. It reads through OAM, checking which sprites will be on this scan line. It chooses the first 8 it finds that do. If 8 sprites were found, it checks in a wrongly implemented fashion. Cool. For further sprites on the scan line to see if the sprite overflow flag should be set. Using the details from the 8 or fewer sprites chosen, it determines which pixels each has on the scan line and where to draw them. During all visible scan lines, PPU scans through OAM to determine which sprites to render on the next scan line. Okay. Sprites found to be within range are copied into the secondary OAM. Okay, that's new. Which is then used to initialize 8 internal sprite output units. OAM NM below refers to the byte at offset 4 times n plus m within OAM. Byte m of sprite n. Okay, so during each pixel clock, the PPU accesses OAM in the following pattern. This sounds like something where I should probably what am I trying to say here? I think I need to go wider on the queue. I need like a second queue. Because I need to be doing this in parallel. But it doesn't clear on the pre-render line, which is... Oh, 261 is the pre-render line. Okay, interesting. Guess I should have known that. The clear operation is implemented by reading from OEM. Only a signal is active that makes the read always return FF. Okie dokie. I wonder if that matters. Feels like probably not. 32 byte buffer for current sprites on the scan line. Okay, so we need OAM secondary OAM 032 struct PPU secondary OAM 32 kitty. So for the first 64 cycles, that's what we do. Whoops. Okay, do I want a second queue? Do I want to make my queue wider? I think I probably want a second queue, right? Of sprite operations, because there is something being done every cycle, pretty much. Okay, so we can tweak this. I do have time. Okay, good. All right. Let's make a second queue, shall we? Sprite queue. It's going to come above the OAM, and we're going to have a sprite state, which obviously means I should %s PPU state, BG state, capital S, there we go, state G. Okay. And then we need sprite Q, basically the same. Sprite Q, it's going to be sprite state. Oh, and then we should %s PPU op to BG op G. And then this will be a sprite op. Okay. So this will fail to build because we don't actually have that defined yet. Pub enum sprite op. there's a no op. Okay, so this should build, right? Whoops. Nope, super doesn't build. Oh, because I didn't change this name to sprite state. And I didn't change this name to sprite queue. Okay, now you build. You still panic at fetch sprite low, which is fair because that's going to go away anyway. Okay, so. Oh, is this the V blank interval right here? No, that doesn't make sense. H blank interval? Maybe? Well, whatever. Okay, so we've got our sprite op. We're going to do exactly the same thing we did with background ops. Just give ourselves a big old match statement. Match X. Sprite op. Oh, hello. Thank you, Silence, for the raid. That's a surprise. Hi. How's it going? I'm working on a NES emulator in Rust, trying to finish it in less than 2 weeks. So far, things are going pretty well. We're working on the PPU currently. Wait, in Rust, yes. PPU tile scanline. I am lately a big Rust fan. Oh, also I have a cat, and he's running away. Even Poggies. I'm creating a DB in C. Oh, that's cool. I am not one of the Rust people who will tell you you are criminally negligent for writing it in C, don't worry. So what brings you and your raiding party by? Are you just cruising the science and technology section and happen to come across me, or what? I'm not part of the RASF, no. I do like Rust, but you can use whatever you want. No skin off my nose. Okay. Oh, hi, buddy. You gonna jump on my lap? Yes, you are. Okay. Kitty, kitty, kitty. This is my cat. He comes to annoy me when I try to stream. A little lower. Look at the camera, buddy. Okay, he's completely uninterested in y'all. But he's very adorable. Anyway. Okay, so step 1, clear OAM. I just ended my stream and saw that your stream was interesting, so I was like, let's host him because I have no idea what NES does. Yeah, well, I don't have a ton of idea of how the graphics work either, but basically that's what we're working on right now. This is the cycle-by-cycle diagram of how rendering works in an NES, and I'm just trying to go through and implement it. Musin and Creative Nobu helped me out with the explaining. Cool. I will be sure to check your stream out when I'm done, or if I happen to see you on again, because I appreciate you bringing everybody by. Okay. I'm guessing, actually, we probably just want a cycle count for this one. because it's going to be the same for basically every scan line. Yeah, okay, so let's just say cycle. To finish up, in simple terms, basically he's imitating the old console, so his program will act like the hardware. Yes, that's basically it. So obviously these exist. This is one right here, which has a nice debugger, which is why it's pulled up. But basically, if you want to like play NES games on your computer, this is what you would use. And I'm basically going through and implementing everything at a super low level. Because some of these old games really rely on like the cycle by cycle timing of the CPU relative to the PPU, which is basically the graphics unit. And so I'm going through and implementing everything at the cycle granularity, like doing exactly the memory reads, exactly the memory writes that would be done in the actual hardware. CPU cycle. So for cycles 1 through 64, that's what we're going to do. CPU dot secondary OAM. No problem. I forgot to follow what I am now, and I'm going to head out. I got work and got to get this cramp out of my side. Have a good day at work. I hope things go well. And again, thanks for stopping by. I really appreciate that. Anytime anybody decides to stop by is a good day for me. Cycle divided by 2. Cycle plus 1 divided by 2, probably. Yep. Is equal to 0xff. Good kitty. Pixel Q, or not pixel Q, sprite Q. Push front. Sprite state. Op is going to be sprite op. Wait mem. Cycle is going to be cycle plus 1. Oh, and then this needs to do sprite Q, push front, sprite state, op, sprite op, clear, oh, hey, m, cycle, cycle plus 1. If cycle equals 63, do a different thing. Otherwise, do this. And also do this. And then we just do sprite op, wait mem, underscore, underscore, do nothing. Oops. Lost all my alt tab muscle memory now. Sprite state does not have this field. That is true. I changed it. PPU.secondary OAM. Oh, yeah. Okay. Cycle as you size. Yeah, this is not real. Go ahead and get rid of that. Where did I even do that? Oh, up here, okay. Get rid of all this. Go. What's your problem? Fetch sprite low not covered because I forgot to delete it. Okay. Now let's make sure that we're actually going to hit this. Nope, doesn't look like it. Oh, I know why. It's because I'm not actually running the sprite queue at the moment. Let sprite state equals self dot sprite queue dot pop front dot unwrap. Let uop sprite uop equals sprite state dot op. Let ufun and u u16 equal sprite uop dot into ufun self sprite state dot cycle. Go. Wow, 24 viewers. This is probably the most I've ever had. Welcome aboard, everyone. I hope that you. I hope that you're having fun. I hope that you enjoy the stream. If you want to say hi, absolutely feel free to do that. I think that would be what? That would be really cool to hear from some of you and understand how you came to find the stream. I had a little experiment today where I didn't advertise the stream anywhere. Oh, I see what stupid thing I'm doing. It actually wants to be -1, not +1. Fence post error. Okay, much better. Explicit panic. That's what we wanted to see, which means we're hitting this chunk. Which means we need to move on to the next thing, which is sprite evaluation for next scan line. So how does this work? Cycles 65 to 256. On odd cycles, read from primary OAM. On even cycle, write to secondary. Are you hard coding for each cycle? Depends on what you mean by that, but basically no. What I'm doing is I'm writing sort of micro operations for each of the things that happen, right? So fetch a name table byte, fetch an attribute byte, fetch a background byte, fetch the high background byte, and then go through the OEM clear, and then we're just pumping this queue of operations. Is kind of how this works. So we have that's a bad place to look at it. Struct PPU. We have two queues, right? We got a queue of background state and a queue of sprite state. The background state contains an operation and 2 arguments. The sprite state contains an operation and 1 argument. And then we just pump the queue. And every operation, when it is processed, will add 1 or more operations to the queue. And so as long as I do that right, I should have this cycle accuracy that we were looking for in terms of getting everything to line up correctly. So I'm not really hard coding it for each cycle. I'm writing each micro operation, and then depending on the cycle count, I'm gonna like move to a different operation, obviously. So this one ends at the end of cycle 64. We should move out of this sort of quasi state, and so that means that we're gonna move to sprite eval, which is not one I've written yet, but does that make sense? It's like coroutines, but like squished flat, so that I can serialize it and do other stuff like that. I have to fix all of these stupid, unused variable warnings. Right, sprite eval not covered because I didn't write it. Completely fair. Ah, so to get the timing correct. Yep. Because there are games in some of these old systems, including the NES for sure, that have an absolute requirement that you be cycle correct. The infamous one for the NES is Battletoads. Alright, so this should explode. Yep. Okay, so what does sprite eval actually do? That should be described right here. If it's an odd cycle, data is read from primary. If it's on even cycle, data is written to secondary, unless secondary OEM is full, in which case it will read the value of secondary OEM instead. Starting at n equals 0, read a sprite's y coordinate, which is OAM n0, so 4 times n. Copy it to the next open slot in secondary OAM. So y coordinate is in range, copy remaining bytes of sprite data into secondary OAM. Increment n. If n is overflowed back to 0, go to 4. If less than 8 sprites have been found, go to 1. If exactly 8 sprites have been found, disable writes to secondary OAM because it is full. This causes sprites in back to drop out. Starting at m equals 0, evaluate OAM and m as a y coordinate. If the value is in range, set the sprite overflow flag in 2002 and read the next 3 entries of OAM. Incrementing m after each byte, incrementing n when n overflows. If m equals 3, increment n. The value is not in range, increment n and m without carry. If n overflows to 0, go to 4, otherwise go to 3. The m increment is a hardware bug. Cool. Attempt and fail to copy OAM n0 into the next free slot in secondary OAM and increment n, repeat until h blank is reached. Okay. So what we're going to do here is we're going to read. First, we're going to read from primary OAM. So that's what we're going to do. Read OAM. Except I capitalized it elsewhere, so I'm going to capitalize it here. Read OAM. Alright, and then the way that we're going to do that is basically, this is going to be sort of problematic. I'm going to have to add a second argument, which is fine. Am I even using BG low byte anymore? Yep. This is supposed to be BG high byte. Oops. Good thing I'm not actually rendering anything yet. High byte. Sprite count 0. Doo-doo-doo. Okay, so read OAM. Starting at n equals 0, read a sprite's y coordinate. How do you know if it's a sprite? Sprites found to be within range. What range? Reads the sprite list. See if there's something better here. OAM, here we go, that might help. Internal memory, a display list of up to 64 sprites. Each sprite's information occupies 4 bytes. Byte 0, Y position of top of sprite. Sprite data is delayed by 1 scan line. You must subtract 1 from the sprite's Y coordinate before writing it here. Hide a sprite by writing any values in EFFF here. Sprites are never displayed on the first line of the picture, and it's impossible to place the sprite partially off the top of the screen. Oh, so in range is in range of the current scan line. So we do need the scan line, which, I mean, that's not surprising, I guess. So the Y is in range of the current scan line, but we're actually looking at the next scan line because of how this works. We're fetching stuff for the next scan line. So let's do that. I'll just build this and watch where it explodes, which will be lots of places. Scan line. Scan line. Scan line. Scan line. Since we're not going to increment it here, we're not going to increment it in any of these, I don't think. Nope. Okay. Variant or associated item not found in sprite op because I didn't change it. Right, and then this is wrong now. Sprite op now takes 2 U16s. Sprite state dot scanline. And then 273, which is this initialization. Scanline is 0. Although it might want to start at 261. Yeah, because I didn't change this yet. 216. Go, go, go. Choo, 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 choo. Okay, explicit panic, which is what we expected. So now we're going to read the OAM. Let y chord equal PPU.OAM PPU.sprite count. No, that's not right. This is the wrong thing. This is the right thing. Okay. Okay, so N, this is going to be cycle 65, right? Starts at cycle 65. So we want let index equal, we want to get 0 for 65. And then we want to get 1. Well, no, I don't even think that's true, because we're just going to go straight through it, right? This is a real pain in the butt here. This description is not very good. So we read it, and then we either copy the remainder, or I guess we increment n. Or do we read it and then just not copy it? It's kind of a pain in the butt. I was sort of assuming that we would read it. Don't you have to read it because it's dynamic RAM and it will just die otherwise? I guess you have to write to it. Would that be a problem? So we've got, how many cycles? 256 minus 64. That's enough for 24 sprites. But we have more OAM than that, right? We've got 256 bytes, I think, of OAM. Okay, so we must skip, otherwise we would never get there. Or maybe that's not true because it's only 4 actually. So if you've got 256 minus 64 divided by 4, yeah, you got plenty of time. Alright, whatever. Index equals cycle minus 65. Divided by 2, I think. We get 0 for 65, and we get 1 for 67, right? So we'll subtract 1, or we'll subtract 65 from 67, we'll have 2, and we'll divide it, we'll get 1. Okay, that makes sense to me. Let y chord equal OAM index, which just means this needs to be an as you size. If y chord is equal to, or no, because sprites are 8 by 8, right? Yeah, so for 8 by 8 sprites, 8 by 16 sprites, how are you supposed to know? Attributes, sprite priority, X position of left side, DMA, internal operation, dynamic RAM decay. How do you know if it's 8 by 16? Is that in PPU control, maybe? Ignore it in 8 by 16 mode. How do you set 8 by 16 mode? What else could this be in? I don't even know. 8 by 16. Oh, okay, so there is a sprite size in PPU registers. Oh, it's in PPU control. Okay. It had a flag for sprite size under 8 by 16 mode. Yep, right there. Okay, so that's bit 5. Alright. I've got some other stuff that does something similar. Then get sprite height. I guess it's a U16. Yeah, whatever. You're right. Let index equal self dot PPU control, right shift 5 and 0x01. Match index. If index is greater than 0, then 1 is 16, right? Yep. 16, else 8. Okay, so if y chord is greater than or equal to if it's less than or equal to scanline plus 1 and y chord plus self dot get sprite height is greater than scanline plus 1. Let me just think about that for a second. So if the y-coordinate is 5, now let's use round numbers. If y-coordinate is 8, and it's an 8 byte, or an 8 pixel tall sprite, and scanline plus 1 is 8, you want that to be true. So scanline plus height is greater, because it's 16. And scanline plus 1 is 8. Okay, yeah, I think that's right. So then we're going to copy. So we're going to do, we have read OAM, we're going to do write OAM. So first we're going to do the actual copying. PPU.secondary OAM. This is not self, this is PPU. PPU.sprite count is equal to y-chord. And then we need to do the rest of the copies, right? So this is going to be write OAM. Too many commas. He's a good kitty. We're going to do this 3 times, in fact. 3, 2, 1. And we should be able to figure out what to copy from that. Otherwise, we're just gonna wait. Oh wait, you actually can't do this, can you? That's not quite how this works. This is a 3 and this is a 5. Okay, I think I'm maybe making this more complicated than it strictly needs to be. Hi, bud. It's okay. Let me take a look again real quick at the very confusing description of sprite evaluation. So it looks like you want to copy it, evaluate as a y-coordinate. If the value is in range, set the sprite over flag in 2002 and read the next 3 entries of OAM. If m is 3, increment n. If the value is not in range, increment n and m. What? This is deeply confusing verbiage here. I think what this is saying is, look at, I think this is just like repeating itself a little bit. Okay, so cycle mod 4 equals 1. read OAM 4 times n. Cycle mod 4 equals 2. Write secondary OAM 4 times sprites. Cycle mod 4 equals 3. Read OAM 4 times n plus 1. Cycle mod 4 equals 4. Oh, okay, so this is only after you've got, this is only after you've like run out of sprite room. Okay, I understand now. This is in the overflow case. This is the nominal case. And this is how you like know what's going on. Because if we look at the PPU registers, which are around in here somewhere, got too many reference documents open, and we look at 2002, which is PPU status, then we have sprite overflow, which is supposed to be set whenever more than 8 scan lines appear. Generate false positives as well as false negatives. Jesus. So you are supposed to check that every single time. Holy cow, this is banana pants. I can't imagine having me just staring at reference documentation is terribly compelling viewing, but I'm really having a hard time figuring out like what this is trying to say. Badly written documentation. The NES and its not really MOS 6502 are a paragon of design. The 6502 was fine. We finished that yesterday. The PPU is weird. Actually, the 6502 is pretty weird, honestly. It does that whole like partial instruction decode thing that leads to all those undocumented opcodes. Hardware is weird. Nick, did you do an NES emulator? I forget. I feel like you did Game Boy instead. I'm always amazed at the dedication people have when they reverse these early consoles. Yeah, no kidding. We were talking earlier about BU and his work in Super Nintendo emulation. And they decapped chips and did all sorts of stuff. I did NES to some extent and doing GBA. So what is going on here exactly, Nick? Is this just like a really bad state machine that somebody totally effed up in hardware? So the way that I'm currently reading this is, check the Y coordinate. If it hits, copy the data into secondary OEM. Then increment n. Then look at the next n again. And if it's in range, then you set the overflow flag. This doesn't make any sense. I have no idea that PPU is scary. Yeah, it's very weird. I feel like all I did was follow the extensive documentation like a monkey. Is there better documentation somewhere? Because this is garbage. This is terrible documentation. Let's see. Visual to CO2. I mean, that sounds really cool, but also like it's gonna screw everything. Hardware level simulator of the NTSC CPU. Yeah, I mean, that sounds great, but also like I don't want to have to learn how to do this right now. Okay. During sprite evaluation, if 8 in-range sprites have been found so far, the sprite evaluation logic continues to scan the primary OEM, looking for one more in-range sprite to determine whether to set the sprite overflow flag. First select check correctly checks the y-coordinate of the next OEM entry, but after that the logic breaks and starts scanning OEM diagonally, evaluating the tile number attributes x-coordinates of subsequent OEM entries as y-coordinates due to incorrectly incrementing n, which results in inconsistent sprite overflow behavior, showing both false positives and false negatives. Alright, I think I get this now. I've written an Apple IIe Plus in Rust, and using the NES dev docs for the 6502 bit me a few times because the Rico C6502 had subtle differences in a dozen or so opcodes. Yeah, the 6502, much like most of those early CPU architectures, is really less a like coherent architecture as it is a loose idea. Like, hey, this is like a decent way to make a CPU. Do something kind of like this. Like, all right, sure. Okay, so here's what I'm going to do. I'm just going to do it the same way up until it overflows, and then I'll start doing it the bananas way. This description is way better, frankly. As seen above, a side effect of the write signal is to turn writes to the secondary OEM into reads from it. Once 8 in-range bytes have been found, the value being read during write cycles from that point on is the y-coordinate of the first write. Due to a logic area, the result of comparing this y-coordinate to the current scanline number, which will always yield in-range, is allowed to influence the sprite address incrementation logic, causing the glitchy updates. Once one more sprite has been found, another signal prevents this comparison from influencing the incrementation logic, and the bug is no longer in effect. So you check it exactly once, and then you scan diagonally until you get a true, and then it stops happening? Interesting. All right. Okay. So, here's the Earth. Alright, so my plan now is to do so first we read into this section here. And we do PPU.OAM latch equals PPU OAM index. And then we're going to push this one right here. And then sprite op write OAM. It's going to do PPU cycle scan line. And this is where we'll do this bit. I'll go away. Let y chord equal PPU.OAM latch. If it's a hit, write to the secondary OAM. And then we want to push like a read write thing. So this is going to be test sprite, is what this opcode is actually going to be called. And then there is going to be a write OAM. And so what we do is we push read OAM plus 1, write OAM plus 2, read OAM plus 3, write OAM plus 4, read OAM plus 5. Oh, and then this is obviously going to be test sprite. Whoops, whoa, didn't mean to do that. Actually, this is not going to happen because this needs to happen in clear OAM when we break out. Cycle plus 3. So here we're going to do read, write, read, write, read, write. 6, and then we're going to do read again. 7, and then we'll test again instead of writing. So we test sprite 8. Okay, so that ought to work. And then if we don't do that, then we're just going to wait a bunch. So most of these will be null. Oop. So those two stay the same, but instead of this, we do wait mem. Okay, so this is 1, 2, 3, 4, 5, 6 waits, and then you read again. Okay, good. That's what we want. And then we should probably panic at some point. Let's explode on the first sprite hit just for fun, so that we'll know if we ever get a sprite hit. Oh, yeah, okay, 177 as U size. And then I don't think I actually implemented write OAM, did I? Nope. Panic. Yep. Doo-doo-doo-doo-doo-doo. That sure got tall somehow. I'm panicking twice for some reason. Oh, that's at the end of this if. Okay. So then we have sprite op write OAM, PPU cycle scanline. Darn it. Okay, so we know there's been a hit. We did the test. Oh gosh, my leg's asleep, buddy. Sorry. So we did the test on cycle 66, which means that we want, oops, 67 to be 1, 69 to be 2, 71 to be 3. $67 minus 65 divided by 2, or no. 67 mod 64 gives 3. Divide by 2 gives 1. Oh, that's not going to work. It needs to be mod 4 or mod 8. 67 mod 8 gives 3, divided by 2, okay. And then 69 mod 8 divided by 2. 69 mod 8 is going to give 5, divided by 2 gives 2. 71 mod 8 gives 7, divided by 2 is 3. Okay, so that should work. Let offset equal cycle mod 8 divided by 2. Cycle as usize. And then we're going to do a write to ppu.secondary OAM offset, or no, ppu.sprite count times 4 plus offset as usize. More parentheses, more is equal to ppu.oam latch. Okay, and that ought to do it. So that's actually panic there. Well, no, we won't. We'll panic if they get a first sprite hit. What bad thing happened? Expect U8 found U16 because the scan line is a U16, so we just need to convert the Y coordinate. Which actually the Y coordinate, hang on. The Y coordinate must be in tile coordinates, right? Because otherwise that doesn't make any sense. Oh, no, I guess that's fine. Where's the NTSC guide thingy? Because I think there's actually only, like... what's going on? There we go, okay. Yeah, so there's only 240 or 239 visible lines. So that should be good. We'll just cast Y chord as U16. Go! Nope, still problems. Oops, 177. This will be ppu.oam latch. No implementation for U16 plus U8 is probably because I made get sprite height a U8, which it doesn't need to be. Just return a U16. Okay, explicit panic. That's what we wanted to see. Reading OAM index 0. Does that mean we have a sprite hit on the first line? That doesn't seem right. Oh, the OAM is going to be zeros. Where does that get populated exactly? I bet the reset state of the OEM is actually FF instead of 00 or something like that. Where's the like initial state thingy? Do. PPU initial state is in here somewhere. Power up state. OAM is unspecified. Yeah, I mean, I guess that makes sense. What does the init code have to do? Alright. this seems good. So the next thing that we're going to want to do is when we if offset equals 3, ppu.sprite count plus equals 1, also panic. That's worrying. So it shows reading OAM index 0, 1, and 2, but it doesn't show it reading OAM index 3, which it absolutely should. So what's going on here? From clear OAM, when we're done, we push wait, read, test. Alright. Then we should read. I should probably go and delete a bunch of stuff in the CPU that's printing so I can actually read what's interesting to me at this moment. Okay, go. Oh, what did I break? Damn it. Okay. So I'm right, something's going wrong here. Kitty cat. Offset 0, offset 2, offset 3. Well, that doesn't seem like it should be true. So nice job screwing that up. Right OAM. Why do you think there's no closed string? Okay, there we go. So does that mean I'm just calculating this cycle wrong? Current cycle is what? $68. Oh, yeah, okay, that makes sense. -1. That should be better. Read 0, write 0. Read 1, write 1. Read 2, write 2. Read 3. Attempt to subtract with overflow? Oh, because it was 0. Yeah, okay, that's fine. Index out of bounds. Yeah, obviously. Okay, I probably don't want to do the adjustment afterwards then. What I probably want to do is do like cycle as usize -2. Or even -1 would work, but okay, there we go. 0, 1, 2, 3. can get rid of current cycle. Okay, and now we should basically explode. Yep. Index out of bound. Okay, so if if we're done, then we need to start checking for the overflow stuff, which is the weird thing about sprite overflow bug. Okay. So in sprite test, presumably, we're going to want to check if ppU.sprite count is greater than 7. We can't actually do this, but we do need to still check. So this would then set the overflow flag. I should probably do this outside of this because it doesn't necessarily actually matter. Because we need to start looking at other things. Kitty. Let's just make another one. Check overflow. And we can start doing it from down here. So what would normally happen, where do I push that next test sprite? I push it either here or here. And so what we want to do, if ppU.sprite count is equal to 7, else, this is when we want to do this, is if it's not 7. If it is 7, we want to do check overflow instead. And in check overflow, what we want to do is something kind of weird, probably. Okay, sprite op, check overflow. CPU cycle, scan line. Okay. Kitty. Such a good cat. Just chilling on my lap, not trying to eat my webcam. So what we want to do the last thing that we did before we came in here was check overflow. Or was to read from OAN. So if, or well, okay, so we'll do this again. Overflow has occurred. I'm gonna panic here for a minute. If the value is not in range, increment n and m. We definitely are going to explode here, yep. I don't really have an n and m because the read is checked in the good one. Let's do read OAM bug. So what's this about? Once one more sprite has been found, another signal prevents the comparison from influencing the sprite address incrementation logic. So if the value is not in range, increment n and m without carry. If n overflows to 0, go to 4, otherwise go to 3. Okay, so we only scan diagonally until we hit a real startup sprite again. That's what this is saying to me. So, geez, okay. Set the overflow flag. PPU dot. Is that right? PPU control or equal 0x, whatever it is, registers. Sprite overflow is bit 6, which is 0x20. Okay. Remind me what read OAM does. Is it literally just reads it into the thing, right? Yep. So, hey buddy. This is a lot, this whole sprite overflow bug thing. I think I'll probably get this hammered out to the point of like being testable. And then I think I won't actually test it, and I'll test it tomorrow and try to actually display graphics because this is a lot. Head's starting to feel like mushed. So set the flag. What's the thing I was just looking at? Okay, so we are done. We check the flag. If it's set, read 3, increment m after each byte. If the value is not in range, increment n and m. If n overflows to 0, go to 4. So we need some sort of n and m, which we don't currently have. The easiest thing to do is just add them as fields to the PPU struct, which is not like a great thing to do, but oh well. Sprite n, u8, sprite m, u8. And when we book test sprite, or no, not test sprite, when we book check overflow, it's right here, we're going to reset those. PPU dot sprite n is equal to 0, PPU dot sprite m is equal to 0. Or no, that's not actually right, is it? Pain in the butt. Okay. Starting at m equals 0, evaluate OAM and m. So n is not actually 0, n is going to be this ppu.sprite n, except that this is going to be 66 because it comes after. And then I am going to, real quick, because I know that it should overflow sprite n. So I know it should overflow on the very first one, which means that it should be so then it's going to be, n is going to be this, because you got to divide by 2 and then by 4. So we know that it should be 0, 1, 2, 3, 4, 5, 6, 7. So n should be 8 in this case. And if it's not, then we've done bad. So depending on whether we hit the panic or the assert, we will know whether we screwed up. Expected U8, found U size. Okay, fair. Sprite n0, sprite m0. Uh-oh. What's the matter? Oh, read OAM bug not covered. Okay. It's not actually used yet, so we'll just delete that. Uh-oh. Calculated sprite n as something. ppu.sprite n. What did we get? 7? 9? Something else entirely? 7. Okay. Okay. What is the cycle? Oh, you know what? I know what it is. It's because I'm actually going to check on the check overflow section, which is 8 cycles from now. Hey, look, more parentheses. That's great. That's always a sign you're doing something smart. Alright, there we go. That makes sense to me. Okie dokie. So check overflow. Read next 3 bytes. No copy. If the value is in range, set the sprite overflow flag and read the next 3 entries of the OEM, incrementing M after each byte and incrementing N when it overflows. If M equals 3, increment N. I don't really understand that last bit, I guess. Oh, yeah, I guess I do. Who is texting me? Alright. Okay, so read the next 3 bytes and don't copy. We already know how to do this because we do it elsewhere. So read OAM. It's right here. Yeah, this bit. This is what I want. Boop. Alright, so we got read, do nothing, read, do nothing, read, do nothing. So that's 1, 2, 3, and then you're going to do this again. Check overflow, it looks like. Then we need to adjust ppu.m plus equal 4. If ppu.m is greater than 3, ppu.m n plus equals 1, ppu.m minus equals 4. Okay. Otherwise, increment n and m. If n overflows to 0, go to 4. Okay, so ppu.n plus equal 1, ppu.m plus equal 1. If n overflows to 4, if n overflows to 0, go to 4. Oh, except that the read is wrong, so I have to do the read bugged thing, but yeah. ppu.n plus equal 1, ppu.m plus equal 4. If ppu.m is greater than 3, if n overflows to 0, go to 4. So basically if n is 63, or is 64. ppu.n plus equal 1, ppu.m minus equal 4. If ppu.n is greater than 63, then we're done. That doesn't really make sense, but oh, yes it does. It just means repeat until h blank. Okay. Okay, we're done. Field queue with no ops until h blank, which I'll deal with in a second. Otherwise, run this check again after 1 wait cycle. Or no. read again, then run this check again. So we're basically just going to do this, except instead of wait mem, we're going to do check overflow again. Can deal with this in a minute. Panic. Okay, and now we need to implement read OAM bugs, which is going to look a lot like read OAM, except it's going to be a little more complicated. So that's the match, that's the fun, that's the impulse. So this is the comma. Alright, sprite op read OAM bugged. It's going to give us CPU cycle scanline. Read OAM looks like this here. Let index equal PPU dot sprite n plus times 4 plus PPU dot sprite m. All of these need sprite in front of them. That didn't work. It almost, well, it definitely would have been easier to just change it to be M and N. Doo-doo-doo. How's that look? Not gonna run. Definitely I messed up somewhere. 360. Huh, that was relatively easy. Panicked at index out of bounds. Okay. Oof. That's interesting. I think it looks like that because it hit every single time. I wonder what happens here. I guess n increments should all wrap to 63, right? Mod 64. Attempt to add with overflow at 291. Oh, the cycle overflowed. How big is the cycle counter? It's a 16, right? So yeah, we should have broken out by then. Which is interesting, because it means we never hit this. Maybe we need this up here too. What a nightmare this is. Okay, so we panic in here. Oh, because we hit every single time. Like, that makes sense. So there needs to be a check for H blank and stuff, but I feel like this is a sufficient amount of nonsense for today. At some point, we'll fix this transition from out of sprite evaluation and into the sprite tile fetching. But we're going to do that tomorrow. I'm obviously falling asleep, except actually I'm not falling asleep. I'm just worn out from staring at terrible documentation. Thank you everyone for coming by. It really means a lot, especially shout out to Silence who decided to raid me today, which was a big surprise. If you are at all interested in this, I'm going to probably do another 4 or so hours of streaming tomorrow, either pretty early or in like the mid-afternoon. Haven't really nailed that down yet. Again, the challenge here is to complete an NES emulator in 2 weeks or less that is capable of running Super Mario Bros. 3, although sound is optional. I'm hoping that once we get a little bit more fleshed out in this PPU pipeline, we'll actually start putting graphics on the screen, and then we can see, you know, how terrible all that turns out to be. But I'm really enjoying this project so far. I'm really enjoying streaming it for all of you, and again, I appreciate you coming by. And I'll hopefully see you all again tomorrow. Have a good night.